So welcome you to this module. So last couple of modules we were reviewing basic concepts in the problem of hypothesis testing. So we talked about the uniformly most powerful test. Then we realized that in certain situations uniformly most powerful test may not exist. So that led to the concept of uniformly most powerful unbiased tests. And then we did various results which tell us how to find UMP alpha test or UMPU alpha test in certain situations. Now, the need for UMPU alpha test arose because in many situations the UMP alpha test does not exist. So what you do is you restrict the class of tests under consideration by imposing the condition of unbiasedness. After we have done that, my class of tests under consideration has shrunk, and then I try to find a best estimator within this shrunken class, and in many situations it is possible to do so. It is possible to find the best test in the shrunken class. You see, another way to restrict a class of tests under consideration is you impose certain nice conditions on the tests you want to consider. You don't want to consider trivial tests like which always reject H0 or which always accept H0. So one such condition is that you, especially if you have a very nice structure, then you impose the condition of invariance as we did in the estimation problem. So that is what we are going to do in the next couple of modules. So let us talk about invariant tests. So let us talk about, you have a model as follows. So you have x, which is x next to xn. This has a PDF or PMF f, which belongs to some family P. And in the testing problem, what we are interested in, I am given P0 and P1 are two subsets of P, says that they are disjoint. So that means P0 intersection P1 is phi, and their union is whole P. What I am interested in is, goal is to test based on the data, test the null hypothesis H0 that f belongs to P0 against H1 that f belongs to P1. Note that we required P0 and P1 to be disjoint just because of the fact that H0 and H1 cannot be simultaneously true. So that means either H0 is true or H1 is true. So what we are looking for is situations where my problem has a nice structure in terms of invariance. And we have seen in the case of estimation, if this P is invariant, then in the case of estimation, you have a very nice structure. Now for the testing problems, what I would require is I need a group of transformations under which P, P0, and P1 all three remain invariant. So I give a definition, so let G be a group of transformations so what I say is, so let us say when the testing problem will remain invariant. So under G, suppose if I apply G to an observation X, and if the resulting distribution still remains in P0, I will call P0 to be invariant. If I apply any G to X, and if f is in P1, the resulting f is also in P1, then we say that P1 is invariant. So note that what is happening under invariance is P0 and P1 are not changing, because when you apply G to the observation, Gx under H0 is in P0 gx under h1 is in p1. So my hypotheses remain the same. So if hypotheses remain the same, that means in the two problems my decisions should be the same. So that means my test should be invariant, which is equivalent to saying that phi of x should be same as phi of gx. So probability of rejecting h naught when x is observed, or probability of rejecting h naught when g of x is observed should be the same, because my p0 and p1 do not change if you change the x. And so that leads to the concept of invariance. So we say that that the testing problem one is invariant under this given group of transformation G if P0 and P1 are invariant under G. Both are invariant under G. What does that mean? That is if x has a PD of fi, then for every fi belongs to pi, let me call this as, because I want both my p0 and p1 to be invariant. So if x has a distribution fi which is either in p0 or p1, then for every g belonging to gx, for every g belonging to this group of transformation G, y, which is g of x, has PDF, again some fi star, you may call that as g bar of fi, which again belongs to pi only. So if that happens, then I say my testing problem is invariant. Now note that if my testing problem is invariant, my null hypothesis and alternate hypothesis remain the same, because I am saying whether it is x or whether it is gx, the distribution is in p0 or p1, p0 under h0, p1 under h1. So that means phi of x, probability of rejecting h0 when x has been observed, should be same as probability of rejecting h0 when gx has been observed, because you remain in the same setup. So that leads to the definition of an invariant test. In an invariant testing problem, a test phi is said to be invariant if, because I have seen, if you have applied gx, my null hypothesis still remains f belongs to p0, and alternative remains that f belongs to p1. So that whether you observe x or gx, you are still testing whether your resulting distribution is in p0 or p1. So that means my test should be invariant. That means phi of gx, which is the phi based on the transformed variable in the transformed problem, should be same as, these are probability of rejecting h0, this should be same as phi of x, phi of x, belonging to sample space or Rn, and for every g belonging to G. Now then I can talk about, so what it says is if your testing problem is invariant under G, my invariance principle suggests that I should restrict only to the class of invariant test, and then try to find the best test among all invariant tests. So that leads to the concept of uniformly most powerful invariant test, or UMPI alpha test. So let alpha belonging to 0, 1 be a given level of significance, and let di alpha is collection of all those tests phi such that phi is invariant and it has level alpha. That means expected EF of phi x is always less than or equal to alpha for every f belonging to P0. So di alpha is essentially the class of all level alpha invariant tests, be the class of alpha invariant tests. So I can talk about the best test in this class. So that means a test which has the maximum power or the minimum type 2 error, probability of type 2 error. So a test phi naught belonging to di alpha. So that means phi naught is invariant and has level alpha is said to be uniformly most powerful level alpha test, which we in the sort write down UMP I alpha. If it is uniformly most powerful, among tests in di alpha. So very simple concepts. So you define the concept of invariance, then you try define the class of all invariant tests which have level alpha, and then the one which is the most powerful over there, I can call that as a UMP I alpha test. So the goal is to find UMP I alpha tests. Why should I restrict to the class of invariant tests? That is guided by the principle of invariance. So principle of invariance guides that restrict only to invariant tests. Di alpha, and then try to find the best tests over there, and if you can find a best test. Now, like if you see this, when you apply certain principle like sufficiency, sufficiency helps us in reducing the data. So it is basically technique for reduction of the data. Same way, invariance imposes certain condition that you should consider only typical, only those statistics which have a typical structure. Like in the estimation of case, we saw that an estimator is invariant if and only if it is of the type delta naught minus u times some function of d1, d2, dn minus 1. So in that sense, invariance also helps us in reducing the data, the way minimal sufficiency does. So principle of invariance it basically helps us in reduction of data. For example, we saw that there is no need to consider whole sample x1, x2, xn. You consider only those estimators which have of the type delta naught of x1 plus c, x2 plus c, xn plus c is delta of x1, x2, xn plus c. So it reduces the data in certain sense. So the way you had a concept of a minimal sufficiency, I can talk about here the maximal invariant statistic. So you have a minimal sufficient statistic so this is like sufficiency. where sufficiency helps us in reducing the data. Now, when you talk about sufficiency, as you know that there can be more than one sufficient statistics. So the one which gives you a maximum reduction in the data, you call that as a minimal sufficient statistic. Same thing I can talk about over here. Principle of invariance reduces the data. So there could be more than one statistics which have this property that they are invariant. Then the question is which one to use. So here I can talk about the concept of maximal invariant statistics. What does that mean? I'll define in the following a statistic Tx, which is a function of the data, is said to be maximal invariant under the given group of transformations if what should happen? First of all, it should be invariant. If T is invariant, what does that mean? That is, T of Gx should be same as T of x for every x belonging to Rn and G belonging to G. So it is invariant. Now, it is maximal invariant. That means if Tx1 is same as Tx2, that means the two values of the statistics, two sample points fall in the same contour through statistic T for some x1 and x2. That should happen only when x1 is G times x2 for some G. So it is giving the maximal reduction in this case. Because you statistics T partitions the whole space into various parts. And these are the partition sets where T takes the same value. So I look at the partition sets. So the elements in the same partition set should be related through x1 is equal to G of x2. So in such a case, T gives you a maximal reduction in data. Now, I'll do a result which tells you that a maximal invariant statistic is a function of any invariant statistic. Not only that, the distribution of a maximal invariant statistic would depend on a maximal invariant parameter. Now, how do you define a maximal invariant functional? Here I'll talk about functional because everything I'm talking in terms of f belonging to P0 or f belonging to P1. I don't have a parametric model where theta is a real variable or theta is a point in Rn, n-dimensional equilibrium space. Here I'm talking about f, which is a PDF, which is a functional. So I can talk about maximal invariant functional. What would be the maximal invariant functional? First of all, it should be invariant. That means theta of f should be same as theta of what is the group of transformations on the P, that is G bar. So theta of f should be same as theta of G bar f. And it would be the maximal in the sense that if theta of f1 is same as theta of f2, then G, f1 and f2 should be related through G. So this theorem says that the maximal invariant statistic, so let us say Tx is suppose maximal invariant under G. Then the first part says a statistic V is invariant under G if and only if your t is a function of v. So that means, sorry, v is a function of t. So v is same as h of so that is why it is a maximal invariant, not a minimal. In minimal sufficiency, it was happening other way. So what it says is, in a sense, a statistic is maximal invariant if and only if it is a function of any other invariant statistic. Vx is, any other invariant statistic is a function of the maximal invariant statistic. So I say a statistic T is maximal invariant if and only if any other invariant statistic is a function of the given maximal invariant statistic. Minimal sufficiency, it happens other way. I call a statistic to be minimal sufficient if it is a function of any other statistic. Here, any other statistic is a function of a maximal invariant statistic. That is why the name minimal and maximal. Okay, now the second part says the distribution of a maximal invariant statistic would depend only on maximal invariant functional, provided such a functional exists. So suppose there is a functional. What does functional mean? Functional means whose domain is set of functions, because here I am talking about theta of f. So what is the domain here? A function. So such functions are called functional. So functionals are nothing but functions whose domain is a class of functions. So suppose there is a functional theta of f on P satisfying. What does it satisfy? As I say, it is a maximal invariant, so that means it should be invariant first of all. So that means theta of g bar f is same as theta of f. What is this g bar? I have not written down explicitly, but this g bar, because my p0 and p1 are invariant. G is invariant. Sorry, p is invariant under g. If p is invariant under g, there will be an induced group of transformations on the p. So this g bar is the induced group of transformations on p. So if theta of g bar of f is same as theta of f for every g bar belonging to g bar. So what is a g bar? G bar is the induced group of transformations on the set of probability densities P. And second thing is it is maximal invariant. That means if theta of f1 is same as theta of f2, then f1 should be g bar of f2. So if theta of f1 is same as theta of f2 for some f1, f2 belonging to P, then theta 1 should be same as g bar of, then f1 is same as g bar of f2 for some g bar. So what it says is, suppose there exists a maximal invariant functional. Then it says that the distribution of the maximal invariant statistic Tx would only depend on the maximal invariant functional, which is theta f. So then the distribution of Tx, which is nothing but a maximal invariant statistics, depends on theta f, which is nothing but a maximal invariant functional. The same thing one could have proved in the estimation also. In fact, this all discussion holds for the estimation as well. So let us try to prove this. So what I do is, in the first part, suppose v is h of tx for some function h. So you write down for some function h. So I'll first assume that Vx is same as h of Tx, and then I'll prove that V is invariant. So first I prove this part. That means suppose V of x, suppose for some function h, V of x is same as h of Tx for every exploit. So what I have to show? I have to show that V is invariant. Then for any g in capital G, what would be V of Gx? V of Gx is nothing but h of T of Gx. But T is maximal invariant, so it is invariant in particular. So T of Gx would be same as T of x. Why? Because T is invariant. So T of Gx would be same as, and h of Tx is nothing but P of x. So one part is obvious, that if Vx is some function of T of x, then it has to be invariant. Now let's try to prove the converse part. Conversely, suppose V is invariant. What I have to show? If V is invariant, I have to show that V is a function of some function of Tx. Now to show that V is a some function of Tx, what do you do? Or in general, let us say, when you say that f is a function of x, what does that mean? That means if f of x1 is same as f of x2, then x1 has to be same as x2. Or in other words, two distinct points, or the same point cannot go to two distinct points. That means if v of x1 is same as v of x2, then you see, that is what, to prove that something is a function of the, what do you do? Same point should not be going to two different points. That means if Tx1 is same as Tx2, then x1 has to be same as x2. So to show that V is a function of T of x, we need to show that, because to show that it is a function of this, that means if these 2 points were same, this would go to the same point, not to the two different points, right? This is not allowed in the function. It's a function of Tx, we need to show that if Tx1 is same as Tx2 for some then V of Tx1 should be same as V of Tx2. Right? Just by the property of a function, because when you say that a function of f is a function of x, what does that mean is if x equal to y, then f of x should be same as f of y. So you cannot have this kind of a situation. If x equal to fy, that means they are the same point. You cannot have this kind of situations because that violates the definition of a function. So let T of x1 is same as T of x2 for some x1, x2 belonging to Rn. But T is given to be maximal invariant. So if T of x1 is same as T of x2, this implies that x1 is same as g of x2 for some g. Why? Because by the definition of a maximal invariance. But if x1 is same as g of x2 and v is a function, so this implies that v of x1 is same as v of gx2. But v is invariant. So v of gx2 is same as p of x2. And that is what you are required to prove. Now, I'll show that the distribution of T only depends on the maximal invariant functional theta f. So, to show that distribution of Tx depends on the maximal invariant functional, what you have to show? You have to show that if theta f1 is same as theta f2, then pf2 that Tx belongs to B would be same as pf1 that Tx belongs to A. So, to show that, so let me write down about the B part. To show that, what I have to show? I have to show that distribution of T belongs to, is a function of a maximal invariant functional. So, to show that Pf Tx belongs to B, this is the probability distribution of x, is a function of theta f. That means it depends on f only through theta f. We need to show that if theta f1 is same as theta f2 for some f1 f2, then pf1 Tx belonging to B is same as pf2 Tx belonging to B for every Borel set B. All right, that is what you have to show. Okay, now let us try to see. So let theta f1 is same as theta f2 for some f1 and f2 for some So what does that mean? Theta f1 is same as theta f2. That means f1 is same as g bar of f2 for some g bar in g bar. So what does that mean? Then for any Borel set B, let us consider Pf1, the Tx takes value in B. But I know that my f1 is same as g bar of f2 because theta was maximal invariant. So this implies that P of g bar of f2 Tx belongs to B. But I know that my set of probability distribution is invariant. So whether I take my PDF to be g bar f2 and talk about Tx belonging to B, or I take here f2 and I can make it here g bar of g of x because of invariance. So this is same as P of f2 because g of x has distribution g bar of f2. So when x has g bar f2, which is equivalent to saying that gx has a distribution f2. But T is invariant. So this is same as P of f2 Tx belongs to B. And that is what you are required to prove. So if you see last theorem, what it suggests is any invariant statistic is a function of maximal invariant statistic. And B says distribution of any maximal invariant statistic depends on maximal invariant functional. So indirectly we have proved that distribution of any invariant statistic depends only on the maximal invariant functional. So distribution of any invariant statistic Vx depends on maximal invariant function. For example, if you try to see, recall your estimation theory, your any invariant estimator was a function of x1 xn and x1 minus xn, x2 minus xn, and xn minus 1 minus xn. Maximal invariant functional there turned out to be theta 1 minus theta plus c. In fact, maximal invariant was constant over there. So it was not depending on anything. So what would happen is, in many situations, that means when I am restricting only to invariant tests, I would be restricting to, because invariant test would be an invariant statistic. And so their distribution would depend only on the maximal invariant functional. So in many situations, this maximal invariant functional would be a real valued parameter. So my whole problem test, and it may be possible that I am able to convert my original hypothesis in terms of this theta. And so the best test may exist within the class di alpha. So let me stop over here. We'll continue from here in the next module. So thank you very much for your patience.